Peter, did you bring enough donuts for everyone?
Yeah. When I made this picture, I was head of the safety committee or something like that at both the university one as well as the safety czar for the department.
Oh, you mean you're allowed to drink coffee in the lab?
No, you're not. That's the you're definitely not. No food or drink in laboratory spaces. So. I think I just saw Rolando Valdez Aguilar, who was my postdoc at the time when I made this picture, and I think I told this story.
Yes, I remember this.
I remember Rolando said, "You're in charge of safety?"
That's funny.
Should we wait 1 or 2 more minutes, Chimal?
Sure. Yeah.
We have more than 60 already. 62.
Yeah, give it 1 minute.
Okay.
You're not seeing the slide with the presenter notes, right? You're seeing
No, the regular mode.
Just the regular one. Good.
Yeah, we're recording it as well. Yeah.
Yep. Yeah, but I just wanted to make sure I shared the right screen. That's all.
Mm-hmm. Okay, 74.
75.
That's your criteria, Pension.
76. Okay, so maybe let's just get started. Yeah, so we're very glad to have Peter Armitage from Johns Hopkins University to talk about the electrodynamics of topological materials from free fermions to strongly correlations. Okay, yeah, it's all yours, Peter. Thank you.
Yeah, okay, thank you very much, Pencheng. So yeah, and thanks very much to organizers for putting together this meeting, both the one that we're having now and then the one we'll have in the fall, fingers crossed. It's great to see a lot of old friends on the call and people whose names I know, as well as a lot of course, also great to see names that I'm not as familiar with. So I was asked to give a kind of an overview of experimental matters associated with topological materials. The goal of this workshop and the goal of some recent efforts is starting to move beyond the perspective of free fermions. Most of free fermion approaches to topological materials, most of what I'll talk about today is in the context of free fermions, but at various points I'm going to kind of try to generalize that to talk about what we might find in cases of both intermediate level interactions as well, in some cases of stronger interactions. But that is less of my talk is about that because this is very much the frontier, trying to understand the role of strong correlations as applied to topological materials. I'm going to talk a little bit about my own work, but I'm also going to talk more broadly about the kinds of things that the community has found and is interested in. And since it's a lot of material, it's not going to be very deep. I'm going to give you a rough feeling, but if you'd like to know more, I'm happy, of course, to give more info. Before I do that, let me thank the various people who have made this possible. In fact, many, many more people than I'm just showing here, but these are just some of the highlights. I'll show you some data from my former student, Bing Cheng, who's now a postdoc at Stanford. My former student, oh my gosh, it's mislabeled here. This is Liang Wu, who's my former student at Johns Hopkins, who's now an assistant professor at Penn. I don't know how that happened. Mintu Mandal, former postdoc. I couldn't say enough nice things about my long-term collaborator, Shanshik Oh, who grows the world's best films of bismuth selenide. Current student, Deepanjan Chaudhuri, who's worked on various aspects of these systems as well. Suzanne Stemmer, a great collaboration on cadmium arsenide films with Suzanne. Materials on praseodymium, films of praseodymium iridate came via collaboration with Mick Lipna and Satoru Nakasuchi at ISSB. And this is where I'll end up the talk today on this oxide system that is maybe one of the first examples we have of where strong correlations and topological semimetals may really intersect outside of the kind of Kondo regime. And I had good collaborations, I'm not going to show this data so much, but with Matsunaga, who is at ISSP, where I spent sabbatical 2 years ago now. Okay, so I'm going to give you my conclusions in advance because I invariably will run out of time. I'm going to talk again about give you a broad perspective on these things. And when we talk about the electrodynamic response or the response of topological materials to fields, of course, the quantum Hall effect is our great aspiration. We want to find things that are like the quantized Hall response, but in other material systems. And so there are not very many examples of this, even proposed as how we might find such things. But there is one, and that is the quantized magnetoelectric effect in topological insulators measured in my groups some years ago. So I'll tell you a little bit about those measurements. Move on to other topological materials, mostly in the context of what we might call topological semimetals. And these are primarily Weil and Dirac systems, and tell you a little bit about what one looks for, how you're trying to characterize materials like that in terms of the optical response, signatures of linear dispersion, the various kinds of novel transport mechanisms that you can get in such systems. This is the famous chiral anomaly. And then what is, I think, very, very interesting work that's been done, not by my work, I'm not going to show you data from my group, but from other groups about nonlinear responses of these systems. And I think this still is a very promising area, but it actually shows, I think, the difficulty of trying to understand what to measure in material systems where interactions may be important. And non-interacting fermion perspectives indicate that one should see quantized things like photogalvanic effects, nonlinear responses, but interaction corrections destroy this quantization. And so this really shows us I think the necessity for coming up with kind of clever schemes for measuring and looking for novel phenomena. And I'll tell you a little bit about quadratic band touching systems, which I think is an area which we understand some things and we don't understand other things, but where the idea of strong interactions and topology or topological adjacent phenomena come together.
Sorry, Peter, do you mean Luttinger semimetal or Luttinger liquid?
I mean Luttinger, thank you very much. That's another, I was just writing these out last night. I mean Luttinger semimetal. Thank you very much. Yeah, that's a mistake. Not a Luttinger liquid. It is a liquid, but not a Luttinger liquid. Thank you, Matt. Yeah, Luttinger semimetal, which is a reference to a particular non-interacting Hamiltonian of two bands that touch, but in a quadratic fashion. Thank you. Okay, so we're talking about the correlation spectrum here and correlation spectrum for topological materials. And just to kind of set the stage, I want to make some distinctions, if you will, between what might be three classes of interacting systems on, which again is across this correlation spectrum. And in the first category, we have what we can refer to as, let's say, non-interacting fermion systems, which are well described by band structure effects. And this is presumably because either the residual interactions in the systems are weak, or you have systems where interactions are not necessarily small, but where the system is protected by some kind of gap in the system. So presumably integer quantum Hall systems fall in this particular category where interactions are not important. One has another class of systems that one might call interaction corrected systems. And this will become relevant when we talk about the Weil and Dirac semimetal systems, where we think interactions don't fundamentally change the character of the state, but interactions are not so small that they don't change the actual numerical values of response functions that we might measure, where we might, again, and I just referenced this, where we might have some kind of quantized response, but this quantization is destroyed by a number of effects, and one of the effects that can be destroyed by interactions. And so there's theoretical work in this regard now. And in fact, experimental work shows that these kinds of effects looked for so far experimentally are not quantized. And then there's a whole third category, which is essentially, I'm not defining very well, but where we have, let's call it just strong interactions, where we have no non-interacting reference point. And the tools that we have generally don't work well for the third category. This is a category where topology is important or not, depending upon what we mean. And of course, what we mean by a topological system is, of course, quite variable. There are many systems which we would characterize as topological spin liquids, which of course, these are also moninsulators. And so of course, interactions are important. But generally what I'm going to be discussing here is materials and considering is material systems where we think about topology in terms of the electronic degrees of freedom, or where the elementary excitations of the system are at least kind of low energy electron hole excitations, or their counterparts at surfaces. So I'm not talking about topological systems in the context of magnetic systems like spin liquids, but of course, these are interesting too. Now, so how can we find and study topological faces? And of course, in general, angle resolved photo emission has been paramount in this search, particularly in recent years. I don't have anything against angle resolved photo emission. Some of my best friends do angle resolved photo emission. I did my PhD using it, but I would say this: most of us became fascinated by condensed matter physics, by the remarkable phenomena that these materials have, by the things they do. And we want materials to do something interesting. We still study superconductors because superconductors are cool. The quantum Hall effect is cool. And in this regard, I think it's a paradigm for the kinds of things we're looking for. We want to look for materials which show macroscopic quantum mechanical effects. That's one of the things that we're interested in here. And in this regard, the quantum Hall systems, I think it's fair to say, is still kind of a reference point for many of us in the field, the integer quantum Hall effect, for looking for the kinds of things that we would love to find in such materials. And so most of the talk today is going to be about the electrodynamic response of these materials, the response to these systems with, let's say, finite frequency light. But of course, the most famous example is just this, the quantum Hall, which is exemplified by its response to a DC current. The quantum Hall, the Hall resistance is, of course, the constant of proportionality between DC current and the transverse voltage. And famously, we find that the Hall resistance is quantized to parts in millions, perhaps even billions, given by this simple formula here: Planck's constant divided by the electronic charge squared, divided by an integer. And this is ideal, of course, and we would love to find quantized responses that are in the spirit of this. And unfortunately, as far as I know, there's only one other example, either proposed experimentally, which can be attempted and has been shown experimentally, and that's the quantized magnetoelectric response of topological insulators. But again, we should keep it in mind, this is the kind of thing we're in general looking for. We're going to be looking for signatures of topology in response functions in other contexts, even if those response functions are also not quantized. But of course, the quantum Hall effect is our standard. Now, with regards to these quantized responses, again, in the spirit of the quantum Hall effect, we can ask about topological insulators. If they're materials that are kind of like quantum Hall systems, what can we measure in them that's quantized? And it was pointed out by Sucheng Zhang and collaborators, and by Joel Moore and David Vanderbilt and collaborators, that we should regard topological insulators as magnetoelectric materials, but with quantized response. Okay, so what's a magnetoelectric? So it was first pointed out by Jalashinsky in the late 50s that certain materials that had point group symmetries, where materials broke both inversion and time reversal, allowed this kind of mixed magnetoelectric response. So you could apply a magnetic field and get out an electrical polarization, or apply a electric field and get out a magnetization. And these can be both spin or orbital response. The most common of these materials is this chromium sesquioxide, Cr2O3. So it's the same crystal structure as sapphire. It's a beautiful green color. It's in fact used as pigments. Many green plastics are actually colored with chromium sesquioxide. So it's a common material around us, and it's a magnetoelectric. You measure it. You can imagine doing a little experiment just like this, running a wire around a piece of chromium sesquioxide, putting a magnetic field in it, and measuring the electrical polarization. This constant of proportionality is just some number, not an interesting number, but a number in principle you could calculate if you had a good enough theory. Okay, so it's also a possible rock. You can find it as a mineral. Topological insulators are proposed to be magnetoelectrics with a quantized response, where that number, which in chromium sesquioxide is just some number, which again you could calculate if you had good enough theory, is actually a universal constant of nature in very much the same fashion as the quantized Hall resistances. And you can kind of see this. This is a bit of a thought experiment here, but imagine we had a slab of topological insulator, and it's a thought experiment. So I'm going to arrange some magnetic field that is pointing everywhere out of this topological insulator. And we know topological insulators have surface states. Right? The insulators in the ideal, they're insulators in the bulk with the surface states, and we make this magnetic field everywhere pointing outward. And we assume we're going to make that magnetic field strong enough to create a quantum Hall effect in its surface. Now we can imagine a situation where we drive, let's say, apply an electric field because of the quantum Hall effect on the surface. This results in a circulating current around the sample in this fashion, a circulating surface current. And a surface current can be related to a bulk magnetization in this fashion. And so you have a magnetic field, sorry, a magnetization in the y direction proportional to electric field in the y direction. So this is a magnetoelectric, and indeed this orbital magnetoelectric response, which is given by our old friend E squared over h times n plus 1/2, where n is some integer that has to do with the number of occupied Landau levels on the surface, and this 1/2, which is a signature of the essential, the topological invariant of the material itself. In the formulation of this by Zhang and collaborators, they wrote it down in terms of in this kind of field theoretic language, in terms of this E dot B term added to the electromagnetic Lagrangian. Importantly here, there's this parameter in front, theta, and theta in parameterized in this fashion is an angle. And if a material is inversion symmetric, this theta parameter is quantized to be pi times an integer. It's an even integer in a conventional material, and it's an odd integer in a topological insulator. So this was worked out by a number of people, Zhang and collaborators, and then Joel Moore and collaborators as well. This has been called Axion electrodynamics because of an analogy to hypothetical Axion particle of particle physics. The Axion was first proposed by different names by Pache and Quinn, and Weinberg was given the name Axion by Wilczek. As Wilczek said, he called it the Axion because they cleaned up a problem with CP violation. And as he's written, I called this particle the Axion after the laundry detergent, because that was a nice catchy name that sounded like a particle. And because this particular particle solved a problem involving axial currents. And so this was all worked out in the context, you know, the history here, so the ancient history is worked out, these things were worked out in the context of the particle physics community. But Wilczek pointed out in the late 80s that the existence of axions, real physical axions in the fundamental vacuum, would modify Maxwell's equations in the following form. And so you would get this kind of modified Gauss's law in this modified term here with the curl of B. And one of the things you can see in all of this is this theta parameter I pointed out on the earlier slide. And theta appears only as derivatives, gradients or spatial derivatives in this regard. And so the gradients are found at surfaces. And as I mentioned, if you have a material which is inversion symmetric, the axion angle is quantized in units of pi. And this is what gives you, in this formulation, this quantized magnetoelectric response. So there are a number of different ways that one can measure this. And we measured this some years ago through looking at the terahertz range Faraday rotation. So this is it's a long talk just in itself. I don't want to go through all the details of it, but let me just say that we use terahertz radiation, so pulses of terahertz light, shining them on slabs of topological insulator, thin films of topological insulator in magnetic field, and very accurately measure the rotation of the terahertz light as it passes through the material. That rotation of light is set by the fine structure constant of free space. And so this is data here. This is the Faraday rotation measured as a number as a function of frequency. Right here is at some small applied magnetic field. And this is some movie. You see this kind of threshold behavior. That's 0, the dashed line. And this kind of threshold behavior moves through our spectral range and passes out to the high frequency side, leaving this low frequency response, which exists on this dashed line, which is set here by this particular expression, which can be shown as indication of this axion response I showed you on the previous slide. Look at different materials, and again, this is a long talk just in itself, and so I don't want to go through all of it, but look at different materials which have different charge densities, different numbers of occupied Landau levels on their surfaces, but they all show signatures of this response in that fashion. And let me just kind of skip to the next slide here, that what we measure essentially is this quantized angle, and we can measure the densities of these systems separately and measure the filling factor on the surface. And so the quantization values are set by these This is, if you will, some measure of the ratio of the surface charge density to magnetic field. And this is this kind of combination of integers that one finds by the tangent of the Faraday angle would be equal to this expression in this fashion. And one finds that they all sit not on the black dashed line as they would if this was a 2D electron gas and had a conventional Hall effect in it, a conventional Hall system, but instead the line is kind of shifted up by exactly 1, which comes from the contribution of the 1/2 and of both surfaces in this fashion. So this is again consistent with the topological magnetoelectric effect. I'm happy to talk more about the details of this. This is not consistent through some of the details. It's not consistent with this just being this usual effect of a 2D electron gas, if you can imagine doing a kind of a similar experiment on just a conventional quantum Hall system. And one of the aspects of this is just that it shows this kind of notable shift of the quantizations from sitting on the diagonal line where they would shift, they would sit if it was, again, a conventional parabolic bands in a 2D electron gas. Among other things, one of the things you can do with this is come up with a purely solid state measure for the fine structure constant. So accepted value for the fine structure constant is 1/137.04. That's measured in atomic physics to some very, very high accuracy. And we don't do quite as well as the atomic physicists do, but the error here is in the 4th decimal point. And so that's pretty good, I think.
Peter, could I, could I ask just to clarify?
Sure.
When you showed the original, the raw data, it doesn't look like anything was quantized. But then when you plotted them on that other plot, right? Yes. So, yes. For instance, this sequence of curve. Yeah. How do I mean,
so you see that the low frequency values here. Mm-hmm. So you put a magnetic field on this system, and because there is finite disorder in the system, you kind of have to increase the strength of the symmetry breaking potential above the strength of the disorder. You push at low magnetic fields, we don't have this system. It's better to think of this system not as kind of quantized magnetoelectric. The surface is not gapped as it needs to be. You put a large enough field on it, and you put a small field on it first, and you make kind of what we should think of as cyclotron resonance in the surface, semi-classical response. As the field increases, that response, that cyclotron resonance, goes to high frequency, and it leaves behind at low frequencies. You can see on, say, these purple curves, which exist along this dashed line here, these purple curves here. And so this is set by this quantization condition, if you will. So that's the data that I'm looking at, kind of neglecting the high frequency stuff, which is in the semi-classical response limit.
I see. And then in the next plot, when you show multiple plateaus, that's what, for even higher magnetic field or different number of layers? Oh, there's a different number of layers here.
Different number of layers, which ends up changing the effective density of the material, the effective number of charges on the surface through effectively band bending effects.
I see. So in this case, is the understanding that it's, you see the way Shuqing Zheng and company and Joel Moore would write down the theta term for Axion electrodynamics, that would be something that happens in the bulk. And yes, there is manifestation with on the boundary, but in principle, if you imagine measuring Faraday effect even in sort of infinite volume, we should still see this effect. But here it sounds like it depends on the number of layers. So is that a surface effect with some
so the when one is thinking about the electrodynamic, so one can always you can go back and forth between the language of surface effects or bulk effects. And from the equations of motion I showed a few slides ago, the reason is because the only way Maxwell's equations are modified is through these gradients or time derivatives, right? And so it's an effect, despite the fact that we should think of it as indicative of the bulk physics. It manifests itself as the surface, and we can always write it as a Hall effect or as a quantized Hall effect, but you need to write it not as an integer Hall effect, but as 1/2 times e squared over h, right? And you can't write down a 2D model. You're limited. If you have a gap system, you're limited to integers times e squared over h.
Yeah, I see now what you're saying, right? So formally, the theta term is a full derivative, and you only see its presence on the boundary. It's a bit like what you said is true also for quantum Hall, right? Where you could think in terms of the currents, the hopping orbits on the edge, or you could think in terms of the bulk.
Yeah, that's right. And depending upon what bit of phenomenology you wish to describe, one picture can be better than others.
Wonderful, thanks.
I don't have the data here ready, but one of the things, for instance, that in the interest of time, let me just go on. But one of the things that you can show, for instance, so these fields are something of order, say 4, 5, 6 Tesla, something we're using here. There is no DC quantum Hall effect in this regime. And that's very much because when you put a magnetic field through such a system, you kind of have, let's imagine you have on this film, you have side surfaces, which are seeing just this kind of sideways field, and those are not getting gapped out. And so they end up shorting out a Hall voltage if you would try to do a DC Hall effect experiment. In contrast, we come in with a kind of a spot of light in the center of a film, far away from these non-chiral side surfaces. Okay, let me go on. Okay, so with regards to Dirac and Weil semimetals, then we have a number of different things that we're interested in here. One thing that I like to point out is the possibility that point group symmetries could stabilize touching degeneracies is in fact far older than the current era. There's this remarkable paper, which is 41 years before the paper of Young and others at Penn, Jean Malie and Charlie Kane, that proposed the stability of Dirac semimetal systems. And so you can see Abrakossov wrote in 1971, the possibility of contact of the conduction band and the valence band at a single point is investigated within the framework of the one electron problem. It's shown that the symmetry conditions for the crystal admit of such a possibility. Right? So we're going to come back to this paper a little bit farther on. There are a number of different things that you can look for in the optical response of such systems. One lesson is provided to us by graphene. And this is data from Gein's group some years ago that showed that the light transmission through a single sheet of graphene is set. So if we take this as the 100% level, the difference from 100% is set by alpha, the fine structure constant, times pi. And this comes from a perhaps unavoidable set of cancellations. If we have, let's say, this is in not the Hall resistance, mind you, this is the longitudinal conductance, or the Hall, it's not the Hall conductance, the longitudinal conductance. If you will, there's Fermi's golden rule approach. You can think you have a matrix element times some joint density of states. And there's a bunch of non-universal factors in both the matrix element, velocity squared, and the joint density of states, which goes like 1 over velocity, and some factors of omega, and everything cancels each other to give you this quantized longitudinal conductance. Okay? In the 3-dimensional Weil and Dirac systems, you pick up an extra factor that goes like omega over the Fermi velocity and the density of states, the joint density of states. And so it's predicted that the optical conductivity goes linear in frequency, which is slope, which is set by the Fermi velocity. Okay, and this is again one thing we have to keep in mind, and I'll come back to this point, is that this is all derived in the context of non-interacting fermions, and in fact, it's believed that the interaction corrections to this kind of effect can be quite large. This is a bit of a cherry-picked data right here, because despite the kind of seeming ease of seeing such a response for the interband transitions in Weil and Dirac semimetals, it's actually very seldom seen. So there's very few cases where people have seen this linear frequency dependence over a very large range, and I think that's because quadratic corrections destroy this, interaction corrections, quadratic corrections to the band dispersion destroy this, interaction corrections destroy it. So one needs to be careful. What we might be interested in is effects which are really endemic to the topological state itself. And so we did some work on cadmium arsenide in recent years. This is a Dirac semimetal system, and for the current purposes, one can think of it as kind of 2 copies of a Weil system with positive and negative nodes on top of each other and prevented by gapping from the crystal point group symmetries. So this is the kind of thing that one is concerned with. This is a plot of the optical conductivity measured in the terahertz frequency range as a function of frequency. This is high temperatures. This is low temperatures. As you cool such a system down, you end up freezing carriers out, and the overall size of the optical conductivity comes down. So we're going to be interested in this kind of Drude-like response here, this downward sloping line. This little bump is a low frequency phonon. Lots of heavy atoms in cadmium arsenide, so the phonons are low frequency, and a very complicated crystal structure, which folds back acoustic modes to the zone center, so which could be seen in the phonons. Now, one of the things that people have been very interested in here is this idea of the chiral anomaly, which is this kind of unique transport phenomena that is proposed to exist in Weil and Dirac systems. And so if I have a massless Dirac fermion, this is for just a single node, let's say, in 0 magnetic field. and I apply a magnetic field, I get Landau quantization in 2 directions, but the third direction keeps its dispersion, but with a twist that you form this kind of one-way going so-called chiral level here. So this is if I put a magnetic field in the z direction, this is a dispersion which is running in the z direction. You can kind of think of it as a flux tube that the dispersion is retained along the direction of the magnetic field in this regard. If we flip the field, the direction of this velocity swaps. So it depends upon the different chiral nodes will have different velocity directions. There's kind of velocity swapping, if you will, between positive and negative chiral nodes in the vial semimetal. Of course, in a material, you don't just have one node, you have to have 2, and then these are typically connected underneath in this fashion. And the idea of this chiral anomaly, it's a unique form of transport in these materials, where the current will be proportional to the magnetic field squared. And with an electric field, it's a linear electrodynamic effect where we're pumping charge from one of these nodes to the other node. There's some complications that come in a Dirac system because we actually now have 2 sets of nodes on top of each other, but they end up being, if I can kind of imagine pulling them apart and I'm displacing them separately here, for this chiral level is for one of the sets of positive and negative, it's connected below, and for the other set, it's connected above. The pumping basically happens in exactly the same way for a Dirac semimetal. And it turns out that well, many people have looked at this, and it ends up being quite challenging to look at this with DC transport. There's been some very heroic efforts recently by various groups. This is some data from Ong's group, but the problem is that in many cases you get an effect of what is so-called current jetting, where if you inject current in a material which has a very large magnetoresistance like this, the current, if you imagine in a particular case here, this is simulations from Elena Hosinger, where the different simulations for different amounts of resistive anisotropies, current injected just in one point just kind of goes straight a shot as a jet to where the current is pulled out at the other node. And you put contacts on such a system in some kind of Hall-bar geometry, and it'll look like there's an apparent decrease of the resistance, but really what's happening is just this narrow jet of current that's flowing across. These optical experiments are in fact much better to do in this regard, I think, because one doesn't have any of these problems with current inhomogeneities. You illuminate the whole sample with light and see the radiated signal. And I'll just very briefly show what we see here in this. We apply a magnetic field in the direction of the electric field. This is the terahertz conductivity as a function of frequency. This peak, that's that phonon that I talked about. But one of the things that I want to point out is that we apply a magnetic field. What you see happen is just the low frequencies change, right? So the overall shape of the curve isn't changing. There's no kind of increase of overall spectral weight. There's not a Drude response, which kind of narrows or broadens in some fashion. It's just the changing of the low frequencies. And in this regard, we can identify it just with the appearance of a new transport channel. Calculations of Anton Burkhoff, which are shown here on the right, show this is exactly what is expected in such a situation where when you apply the magnetic field, the chiral anomaly appears as a new mode of transport, which is essentially, again, this chiral Landau level in the intrinsic suppression of scattering, which happens in this chiral transport. This width of this peak right here is a direct measure of this chiral scattering rate, the rate that chiral charges relaxes between nodes.
So Peter, can I just,
Mhm.
so this is a terahertz and then lower frequencies?
What's that? Terahertz, yeah. So when we say terahertz, we generally mean, terahertz and then down to, let's say, 100 gigahertz or something like that.
And that's a range that's being covered.
That's the range that's being measured here, yeah.
Thanks.
So Peter, did you say you do not see a Drude peak, or you do not expect it because it's a technically semi-metal?
No, this is a Drude response here. So this stuff in purple here is the Drude response of the system. They're sitting on top of it, a phonon.
Gotcha.
And
So
we're just seeing the superposition of the two of them, but it's a semi-metal, but it's a doped semi-metal. So there's a finite charge density with a finite Fermi energy. And it gives a Drude response. So, what we're looking for is the topological response in this ungapped system.
Right, so I follow you. So now if you were to imagine you had a data to high frequencies, you will integrate under the entire Drude peak. So then by the sum rule, how should I think about reconciling the sum rule with the fact that now you have this extra bump at finite field, right?
Yeah.
That it means that
So,
there's
well, one
more
of the things you
electrons.
can see here, for instance, in Anton's calculation, you can see that. So this is the Drude response in zero magnetic field, and then you put a magnetic field on it, and this little bump shows up here. Whoop, excuse me. But you can see the blue curve comes down just a little bit.
Oh, okay.
And so that's reconciling the sum rule here. His calculation was done in the limit of infinitely high Fermi energy. So that's a bit of a detail here. And I don't think that there's actually a general theory for how this is all worked out. One thing you could imagine a system where the chemical potential was really just at the Dirac points. So there's no Drude response then.
Mm-hmm.
Then you apply, then you kind of do your experiment and you pump charge from one node to the other, and you'll acquire a Drude response. It'll be sitting by itself because you'll have no background Drude.
Mm-hmm.
And so you'll kind of be pulling the Drude out of something. Where does it come from? Well, the spectral weight will come out of what was formerly the interband transitions. And so you get there's a kind of a different phenomenology expected where, let me put it like this, where you pull spectral weight from depends where the Fermi energy is before you start pumping charge.
I see.
So if the Fermi energy is very, very high,
mm-hmm.
then you pull spectral weight from the Drude response, the kind of pre-existing Drude response. If the Fermi energy is at the Dirac point, then you'll pull the spectral weight from the interband transitions.
I see. And in your experiments, is the material self-doped? Is the way to put
Yeah, that's right. Yeah, all semimetals have, just through chemical inhomogeneities, end up having some small amount of dopants.
Excellent. Mm-hmm. Thanks.
Okay, let me skip this in the interest of time. So one very interesting development in recent years, and which has been looked at quite a bit in the context of Weil and Dirac systems, is the role that optical nonlinearities may have to play. And so there are many kinds of possible nonlinear responses in materials: second harmonic generation, DC rectification, third harmonic, higher harmonics, difference frequency generation, various kinds of nonlinear absorption processes. This is an old field, but in recent years, I think it's fair to say that there's been new life injected into it by the realization that nonlinear responses in general are sensitive to Berry phase structures and band structures. And so one has, for instance, this is the expression for the Berry connection here, and one can show how it's related to some expectation value for charge in a unit cell. One can show that, for instance, that the nonlinear photocurrent in this regard is sensitive to this Berry connection in this fashion. There's a bunch of kind of older papers, some of which anticipated this in other language, some of which actually discuss this in a much more modern context. But 2000, this paper, the John Sipe should get a lot of credit for being rather far-seeing here in writing this paper in 2000, and then more recent papers, also excellent papers by, for instance, Morimoto and Nagaosa, which brought this attention to many of us in this field. The Berry phase structure is evidence in these Chi-2 responses, which are generally second order responses. Oh, I'm missing excuse me, should be E squared right here, this polarization. So the Chi-2 response is a second order response. Chi-3 is a third order response. Many of these systems, the matrix elements for the interband transitions, which are involved in second harmonic generation, are sensitive to these Berry phase structures. And so these are complicated experiments, and they can have many extrinsic effects. There's thermal effects, photogating effects, work function differences between contacts that may be applied to the sample, inhomogeneities, and there are intrinsic complicating effects. There's scattering in system, non-topological bands in many materials, complicated spectrum that require detailed calculations. And so this, for instance, here is work from Joe Orenstein and Darius Trochinsky some years ago, along with his students and Liang Wu, who was a postdoc there at the time. This is the measured, what one refers to as the nonlinear conductivity, and the calculation here is revealed to match the calculated or the measured signal quite well, but one needs to work closely with theorists in this regard. It's not the same thing as just measuring, let's say, E squared over H. in a quantized response function and knowing exactly what you have already. There's a kind of a detailed, complicated spectra which has to be calculated, and then a complicated experiment has to be overlaid with it. Much potentially better is this prediction for the predicted quantized circular photogalvanic effect in vial semimetals. So this is from some years ago, where it was shown that the so-called injection current, which is the current which comes from the time dependence of the change of the current, is proportional to the intensity of the applied field times a bunch of different things. But one of the things that you can recognize in here is the quantity e to the third over h squared. So it's not e squared over h, it's e to the third over h squared. But that's the fundamental quantity for quantization. And it was predicted in the context of non-interacting fermions for vial semimetal systems that have no mirror symmetries, that over some restricted range in frequency that this could, that one would see a quantized response. And so there have been experiments done, which I think, again, very beautiful, important experiments. Thus far, I think it's fair to say that it's now agreed that the quantization is not observed. This is the conclusion reached by two different groups. This is from Orenstein and Torchinsky, and this is from Liang Wu on two different materials, which we refer to. They're like vial semimetals. We refer to them as multifold fermion systems. There's perhaps a little bit of a plateau in this system, but it's very, very difficult in such experiments to see definitively if the signal is actually quantized or not. Quadratic corrections destroy the quantization. This is also now interactions destroy the quantization, as we'll discuss in a moment. And then there are just other very complicating effects that make the experiments hard to do, like understanding exactly what's the size of the absorptions that are inherent from the linear response in the system. These are fantastic experiments, but very hard. Other kinds of experiments that I think are important ones going forward in fields like this are people looking for the nonlinear Hall effect. This was originally proposed as a good measure of the Berry curvature dipole by Soderman and Fu. One very interesting experiment, this is from Jishan and Kinfei Mak at Cornell, where they looked at tungsten telluride, where one looks at the nonlinear Hall effect. So in a material which doesn't break time reversal symmetry, has no Hall effect, but it can have a nonlinear Hall effect, which is a probe of the Berry curvature dipole in this fashion. One of the complicating aspect to a material like this, it's not gapped, and you're really measuring transport properties of Fermi surfaces. And so it's the quantity you measure is proportional to some kind of scattering time. It's very hard to pull out, again, quantized quantities in this regard. Coming to this point about interactions, which is something that we're quite interested in these systems, is I think it was speculated for some years, but there's a recent paper from Joel Moore and collaborators where they explicitly, in a few different ways, Coulomb interactions, Hubbard interactions, show in a continuum model for a vial semimetal, in this kind of continuum model for a vial semimetal, other known corrections like quadratic corrections and things like this are known to be absent. But they show that there are corrections to the quantized circular photogalvanic effect, which are of order the effective fine structure constant in this system. So not using the speed of light, but using the Fermi velocity, right, which is of course quite a bit smaller than the actual speed of light. So these these interaction corrections can be quite large in these systems. And I think it's at this point, this is all still quite interesting. And I think it's, of course, what hopes is that you can turn this sensitivity to interactions into a tool to study topology and strong correlations in such materials. But I think it's too early to say exactly how that kind of thing would happen. Okay, so what can we do? There's one proposed experiment that has caught my eye here. This experiment has not been done to the best of my knowledge, and I expect that it is less sensitive to interactions because it's kind of based in many ways on a similar ideas that the original ideas about quantum Hall systems were based. The integer quantum Hall effect, thinking about the adiabatic evolution of wave functions under deformation, and it's not sensitive to the precise form of matrix elements. The particular experiment that was proposed here was on for two-dimensional transition metal dichalcogenides, like in the particular case was calculated from molybdenum sulfide, but it's the kind of thing that we should be thinking about. And the experiment is just very simply that you come in with a high frequency laser. And in these TMD materials, you have K and K prime valleys. the Berry phase in these different values has an opposite sense. And you come in with linearly polarized light, make a electron hole excitation. And because you come in with linearly polarized light, the effect is actually the electron hole excitation is actually a superposition of sitting in the K and the K prime values. Linearly polarized light again comes in, makes this electron hole pair. Then you come in afterwards with a terahertz pulse, an intense terahertz pulse, and drive the electron hole pair in real space with the terahertz pulse. They recombine at a later time. When they recombine, they'll emit linearly polarized light. And what was shown in this paper is that the rotation of that linearly polarized light should be precisely the angle of that rotation should be precisely the amount of Berry phase accumulated in this manipulation that comes under the terahertz, if you will, adiabatic movement of the wave functions around under influence of the terahertz pulse. So I think this idea can be generalized to other systems. This is not, TMDs are not topological systems. Of course, they have interesting Berry phase structures, but it could be generalized to those kinds of ones. And so this is something we're thinking very much about in my group, but I don't have any data to show you yet. But my point by showing this is to say that although many of the things that have been done so far, lots of interesting experiments and lots of interesting theory, I think hope is, despite the complications in those experiments, I think hope is not lost. Okay, I want to take, there were some questions. I want to take the final 5 minutes and tell you a little bit about some system where interactions and topology come together, or at least let's say things which are adjacent to topology, and where we might look for materials where we can bring together all of these ideas all together, and where interactions are proposed to be strong. And so this is this idea of Luttinger semimetals, indeed, not Luttinger liquids, as I miswrote on the interesting slide. Thank you, Matt Foster. So I want to come back to this paper, this, again, remarkable paper from 1971, which the possibility for Dirac semimetals was first pointed out by Abrikosov. And in one of the things that, again, he says here that the possibility, symmetry considerations of the crystal admit of such a possibility, basically that even in a Dirac semimetal, even though you have bands sitting on top of each other and forming these degeneracies, they won't gap. He also says that Abrikosov, in the neighborhood of the point of contact, the structure may be linear as well as quadratic. So as long as symmetries are preserved, things like inversion symmetry, that you can have a quadratic touching. And as long as various rotation symmetries are preserved, then you will not gap these bands either. He also says, the role of Coulomb interaction is considered for both types of spectra. In the case of linear dispersion law, a slowly varying logarithmic factor appears in the spectrum. In the case of quadratic spectrum, the effective interaction becomes strong for small momenta, and the concept of the one particle spectrum turns out to be inapplicable. So it doesn't use this language, but in our current language, what we would say is that at low energies, the quadratic band touching system becomes a non-Fermi liquid. Right? That's what's meant here by saying the one particle spectrum turns out to be inapplicable. This is a remarkably modern paper, even if the language is a little bit different from what we would use sometimes. And aficionados of this kind of thing, I encourage you to go take a look at it. The point is that the difference in the spectrum gives differences in electronic properties. And so the fact that one of the ways you can see this, for instance, that things need to be different, if you, for instance, look at the calculated dielectric constant so we can calculate the dielectric constant, let's say, for a linear dispersion versus a quadratic dispersion in the context of some simple model like, let's say, RPA. And if you do so, the dielectric constant for the linear dispersion has this particular form here. This is this logarithm that Abrikosov wrote so disparagingly about in the abstract of his paper. You know, this Landau school didn't like logarithms, or didn't respect them, let's say. But here you see that this particular functional form for the dielectric constant has this really quite remarkable form here. It has, of course, the dielectric constant has a real and imaginary part. It has exactly the same size calculated with an RPA for the real and imaginary parts, and has this form where it goes like 1 over, let's say, the square root of 1 over omega times a bunch of factors here in front. Okay. So let's take a look at those factors just briefly. And I'll just kind of rush through this. If people are interested, they can ask me more questions, but I want to give it as an example of the kind of systems where we might find consequences of strong interactions. So this is this functional form here. And it turns out you can take these constants in here and you can write it as in terms of the Rydberg. So the normal conventional Rydberg, 13.6 electron volts for a hydrogen atom, but now modified by the band mass of the material and by the background dielectric constant of the system. Right? You can look at this. This is for Q equals 0 dielectric constant, but as a function of frequency. But you can imagine other limits as well. You can imagine, let's say, Q equals 0. This is Q equals 0 and T equals 0. And where the Fermi energy is equal to 0, you can write the dielectric constant just as the square root of the Rydberg over h bar omega. Right? A very beautiful functional form. If you are at finite temperature, where temperature is the largest scale involved, you can write it as the Rydberg over the thermal energy. If you are at finite, let's say, large Fermi energy, you can write it at where that's much larger, let's say, than the photon energy or the thermal energy. You can write it as the square root of the Rydberg over the Fermi energy. And if you are at finite momentum, but at low frequencies, you can write it as the square root, again, of the Rydberg over some energy scale here, which has to do with the kinetic energy of an electron hole pair at finite Q. Okay. Important thing in this, particularly for the last form, you see it goes like 1 over the square root of Q squared. So it's really going as 1 over the square root of Q. When you take that and you Fourier transform it, what you'll find is it converts the real space Coulomb interaction, which is usually the bare Coulomb interaction, is of course 1 over r. It converts it to 1 over r squared, which means it scales as Fermi energy as kf squared, which is the same as the kinetic energy itself scales. And those of you who are familiar with things like 2D electron gases and Wigner crystals know that typically when you go to low density systems, that ultimately the potential energy wins, and you form, before you kind of come into a regime perhaps of a non-Fermi liquid type of system, you hit a Wigner crystal, get Wigner crystallization. Here the scaling is such that kinetic energy and the interaction energy are scaling in the same fashion. And it gives you a possibility to come into a completely different regime for strong interactions and in this non-Fermi liquid behavior. And this is essentially, this is my kind of like a very simple version of what Abrikosov was talking about in his papers. And later from that time has been talked about by Youngbaek Kim and Leon Balents and their collaborators. Let me just kind of, again, because I'm out of time and I don't want to go over time, I will just briefly say that what Abrikosov had in mind was systems like alpha tin, a conventional semiconductor with a quadratic band touching. Okay, in alpha tin, it's a semiconductor. The masses involved are small and the dielectric constants involved are large. So the Rydberg itself is a small number, a few milli-electron volts. It was noted some years ago that praseodymium iridate, so an iridate material that many people are interested in studying in the context of topology and strong interactions, which has essentially the same kinds of band structure, which is these two effective J3 half bands touching in the center of the Brouin zone. It's an oxide, so it has much larger band masses, and it has a slightly smaller background dielectric constant. And this pushes the Rydberg up into a much larger 400 milli-electron volts would be our estimate in this regard. And so it's really just a completely different regime for interactions. Abrikosov in his paper says, well, in principle, you would get these interesting effects, but you can never see them because they'll be at such low energy scales. And so you still need to be at lower energy scales and lower Fermi energies than what we've been able to get to. But we see some hint of these interaction effects coming in. And again, let me just kind of run through this. But by looking at the Drude response and a fits to the real and the imaginary parts of the complex conductivity, we can show that there is a very large background dielectric constant in the system, not the background dielectric constant coming from the ions, but essentially the dielectric constant, which is coming from these virtual particle hole pairs that are coming across the quadratic node. And this is a plot of the dielectric constant as a function of temperature here, coming into these very large values of a few hundred at the lowest temperatures. And so these are completely unprecedentedly large numbers for oxides. Dielectric constants of oxides are usually somewhere between 4 to 10 or something like that. And so we believe it's precisely this effect, essentially this effect, which is the predecessor or the precursor, let's call it, of this regime of strong correlations where dielectric constants become very, very large at low densities and are essentially serving to screen the bare Coulomb interactions and allowing you to not get Wigner crystallization, if you will, but coming into a regime of very strong interactions. And one of the consequences of that is that we see this is plots of the scattering rate as a function of temperature And the coefficients here go as the Fermi energies themselves, which we can measure in this system through measuring the dielectric constant. And so you're coming into a regime where we can estimate that the potential energies are about 100 times larger than the kinetic energies involved, some 50 to 100 times larger, which is a regime where you would get Wigner crystallization if this was a normal material, a normal parabolic band. But instead, you just come into this regime of strong interactions. In this case, still a Fermi liquid, but presumably if you could reduce the densities even lower, you would come into a regime where you would be able to measure these kinds of anomalous exponents that were first discussed by Abrikosov, and then more recently by Youngbaek Kim and Leon Balents and collaborators. So going forward, one of the things that we're very interested in here is trying to reduce the charge densities even lower and coming into this regime of essentially completely electronic mechanisms for non-Fermi liquid behavior. And so it's not strictly topology, but it's certainly topology adjacent. And I think that's all I'm going to say. I told you I would kind of go over time, but you've already seen my conclusions. And what I hope, I've given you some perspective on what has been done in the past and what we would aspire to do. We aspire to do things like the quantum Hall effect, but in modern topological materials. But there's not very many examples of how we can do that. We've measured the one system we know how to do, and showed its quantized magnetoelectric response. There are other appropriate response functions to measure in Weil and Dirac systems. Some of these are affected by interactions and some are not. I pointed out a particular experiment that I don't think the consequences of interactions have been explored, but is at any rate related in spirit to at least some of the original ideas about quantization of quantum Hall systems. And then I pointed out the importance, I think, of these quadratic band touching systems and as a platform for strong interactions in topology. I thank you for your attention and apologizing for going a bit over.
Thank you, Peter, very much for this great talk. I'm going to take over moderating the questions in place. So I guess the first question I see is Matt.
Yep. Hey, Peter.
Hi.
So one question, I haven't followed the literature that closely in terms of optical measurements of Weil semimetals, but somehow we ended up doing a calculation of an anomalous skin effect in a Weil superconductor, with the idea being that if you have a superconductor, at least if it's very clean, you don't actually get a response from the bulk. And one thing we found is some kind of funny absorption peak where you can have a transition between the bulk and the surface states. And it's not quantized, there's nothing particularly nice about it, but some peak.
Mm-hmm.
And I'm wondering, has this, and it involves the transitions between the chiral surface states and, the bulk Weil cone state. So I wonder if anything like this has been seen. It would be superimposed on top of the background optical conductivity.
Right, so for a Weil superconductor?
For a Weil semimetals.
Oh, your calculation was for a superconductor though, right?
Yeah, ours was for a superconductor, so we don't have the background. So in a Weil semimetal, you would have this linear and omega background.
Yeah. So I'm aware of no clean demonstration of those kinds of effects, and I remember that you have some predictions for this. One of the things that I would say is complicating about many Weil semimetals that we have is just the presence of other bands around. And so there is, and also non-universal effects. Quadratic corrections in the family of tantalum arsenide materials are huge. And so it's very hard to, I think, unless you see something quantized or have an experiment where at least you're in principle sensitive to those kinds of effects, or sensitive in some way to the adiabatic evolution of a wave packet as you move it around, an example I gave for the electron hole pair under perturbation of a terahertz pulse. It's very, let's just put it that it's very, very model dependent, I think. And
I see.
I hope people will look for what you're proposing. My inclination is that it's hard to come up with anything definitive in the material candidates we have, and I'm happy to be proven wrong.
So one other very quick question, which on different subjects. So with the Luttinger semi-metal, so as you're well aware, in the early days of graphene, Coulomb impurities were a big problem because it would give rise to these electron hole puddles, And a lot of the physics that people wanted to see in terms of hydrodynamics and stuff like this, you couldn't see it when people were exfoliating onto silicon dioxide. So Luttinger semimetal, similarly, as a quadratic band touching, it's it's a low density system, like say in these half Hoyslers and what have you. So do you have to worry about electron hole puddles? Like in this compound you talked about, can it be made clean enough that you don't have to deal with this issue?
I think you probably do have to worry about these things tremendously. The upside and the downside is that the material that we're looking at there is 3D. So it's presumably less sensitive to the kinds of problems that they had in the graphene case, where Coulomb disorder in substrates was a big problem in driving this puddle formation. The downside is that it's in 3D. And so that one doesn't have a knob to gate these systems in the same fashion as you do in the case of graphene. So disorder is, there's also predictions, and I forget exactly where the theory ended up on this, but there's predictions that even without worrying about puddling, but just disorder itself will create a diffusive phase even for kind of zero chemical potential on average. And that's of course, that's of course complicating feature, interesting but complicating. And there's also predictions for effects that are kind of go beyond those of what Abrikosov and then later Kim and Balents considered, that you should get transitions to a mod insulator state for very low charge densities, that ultimately the system would be Igor Herbut has some papers on that. Pallab Goswami has papers on that about transitions to the various kinds of pneumatic orders that will also gap the system in this regard because they're Q equals 0. And so, is that, so if we look for the Abrikosov, the non-Fermi liquid Luttinger Abrikosov phase, and we find instead an entirely electronic mechanism of extended states that allows us to find a mod insulator, well, that's fun too. But we just don't know what happens in real materials, or even for the idealized case. And then you put disorder in on top. Are puddles important? Is a diffusive phase form? Yeah, there's really a tremendous amount to do, and I think it's the important takeaway message is that it's intrinsically different from the Weil linear dispersion case.
Next, I think it's Rolando Aguilar.
Yeah, hi. Peter, regarding this particle hole experiment, so you're talking about a 3-pulse experiment, or is it a 2-pulse experiment only?
Essentially, it's a 2-pulse experiment. So it's photoluminescence.
I see.
It's photoluminescence under with an intermediate perturbation of terahertz. So you come in with linearly polarized light, make this. I don't even need to show it because it's actually a very simple idea, but clever idea. Come in with linearly polarized light. The right and left circularly. You presumably know this, but I'm just being more explicit for everyone else. Linear right and left circularly polarized light couples to the K and the K prime values selectively, but linearly polarized light will make a superposition. The electron hole pair will be superimposed, but then under the 80, then you come into the terahertz pulse, and you kind of just imagine you're moving these guys around in real space and momentum space, and then they recombine. And what you can show is that when they recombine, the light that is emitted after recombination is also linearly polarized, but has its rotation rotated, and has its polarization rotated, and that rotation is exactly the Berry phase, or the angle accumulated under the adiabatic evolution during the terahertz.
And so will this depend on the terahertz polarization?
Well, the details of what you
I'm imagining if
so if you come in with, let's say, a linearly polarized light, then you but if you come in with anything which has a circular component to it, which is elliptical at all, you can imagine you kind of end up somewhere else with the electron hole pair in momentum space if it's there are some effects which come in with linearly polarized light, and I don't recall exactly how that happens now. Mark Sherwin in Santa Barbara has done some work where those effects are relevant in semiconductor quantum wells, where it's sensitive to Berry phase structures. But you can imagine any time where you would come in with anything which is even elliptically polarized, even if some crazy polarization, and then it recombines, you pick up some Berry phase. you may have a hard time reconstructing exactly what the Berry phase structure of the material is, but you'll get some rotation. And presumably if you characterize your terahertz pulse well enough, you can figure out what's going on. And it's my hypothesis that this kind of effects are far less sensitive to interaction corrections than the kinds of effects that people see, let's say, in the photogalvanic effect. I'm sorry.
Right, so
I don't know if you have more to say. I rambled. Go ahead.
No. So I was thinking that the terahertz polarization, in principle, should help figure out the k-space structure of Berry phase. Is that?
That's the idea. Yeah.
That's the idea, right? Okay.
Yeah, that's the idea. Yeah.
All right. Thank you.
Yeah. So what you could imagine doing, let's imagine you had purely circularly polarized light, and you knew what, and you came in with a very distinct photon frequency, so you knew exactly what electron hole pair energy you were making. And then you come with exactly circularly polarized light, you could imagine, but use longer or higher and higher intensities. So this particle pair makes larger and larger excursions as the intensity of the terahertz light goes up. And in this regard, you could map out the Berry phase structure.
Mm-hmm. Okay, thank you.
That's the ideal experiment to do.
Third question, Pavlo Shukatov.
Yes, thank you very much for the talk. I have a question regarding the optical measurement. Is it possible to organize some sort of local measurement where the spot size is very small material? So what are the typical sizes of your laser spot?
So what do you want to do in terms of local measurement?
Well, for example, we can eliminate one part of the sample and measure the response from larger sample, or somehow measure response locally when eliminating only a particular spot. That's why I'm wondering.
Most of the experiments that I discussed, one was thinking about doing experiments in the far field. So you're essentially limited, the probing region is essentially limited by the wavelength of the light being used. It may be that there's something interesting to be done with, there's a huge field of people developing various kinds of near field optical measurements now, which are not diffraction limited. It could be that there's something interesting to do. I don't have any thoughts about that. But generally the experiments that I've talked about here are all limited by the wavelengths of light. And so if you're using laser, 800 nanometers, let's call it a micron. So that's a reasonably small sample. If you're using terahertz, then you're talking about, a few hundred microns. So that's a much larger sample.
Okay, thank you.
Next, I believe TC Wu.
Hi, Peter. So for the second order effect, the photogalvanic effect, I know that interaction can remove the quantization as shown by Joe Moore, but how about the effect of disorder? Is this effect robust against disorder, or can they be killed?
I don't think that these effects are really robust against those kinds of effects there, which are really robust against. They're not really robust against much, unfortunately. I think that in general, if you're in a metal system like this, and you want to look for something intrinsic and quantized, then you essentially need to be probing the system above the energy scale or frequency scales that scattering is important. So as scattering gets larger, you need to go to higher and higher frequencies. So essentially omega tau, where omega is the frequency of your probe, omega tau has to be large. And that's always a complication. So it may be that you could have very clean material and be at maybe high enough frequencies that omega tau is a large number, but still low enough frequencies that you're not hitting other topological bands in the system. That's again an ideal, but that's aspiration.
Thank you.
And then Hanyu.
Hi, thanks very much for your great talk. I have a question regarding the 2 to 7. So here you see that as temperature goes down, the dielectric function diverges. I'm just curious that when the Fermi level goes up, then there's a Joule response as well, right? So at which point the two will be comparable? And only under what kind of doping level would these fluctuation become dominant?
Yeah. So I went through this quite quickly. So in the case of our experiment, we have a Joule response, right? Because the material has some finite amount of doping in it. And then it also has, so that's one contribution. And those are, we can understand that as kind of the real excitations right near the Fermi energy at low frequencies. But there are also virtual excitations which exist in the material, which are one way of understanding their consequences phenomenologically is that they give a dielectric constant, but a kind of background dielectric constant. So the expression we would, for instance, fit to is this one right here. So there's a Drude contribution, and then there's this term here, which is the background dielectric constant. That's always a term which exists in any material because it has to do, in a normal semiconductor or a cuprate superconductor or something like that, you always have some polarizability of the ions there. And so we refer to it as the high frequency dielectric constant. And one way of thinking about it is that it's the dielectric constant at low frequency, which comes from virtual charge excitations to much higher energy states. But its consequence phenomenologically, it's the real dielectric constant at low frequencies due to everything else which is not the Drude. And that's a number again, which is 4 or 5 in a conventional semiconductor. Almost all materials are, there are some funny materials that have large dielectric constants like strontium titanate, but just every material, has a dielectric constant, which is, plastics are a little smaller, but semiconductors and oxides, it's always 4 to 5 to 9, something like that. And so in this regard, when we see 200, we know that we're seeing something else. And so it's an extra contribution, which essentially comes from the virtual particle hole transitions that are coming between these two bands. And you can imagine that, as within some kind of perturbation theory, you have, some matrix elements on top and then an energy denominator. And as that energy denominator becomes really small, then the contribution becomes really large. And so if you have a finite Fermi energy, then that cuts off this divergence at some energy, and it leaves, the lower you make the Fermi energy, the larger this becomes. That's all calculated within some kind of simple RPA, and that picture would break down if you really came with a strongly interacting regime at low energies.
I see. So in this case, it's all this contribution actually dominates the Drude model, which is a relatively small background here.
Well, okay, yeah. So sorry, I didn't answer your question explicitly. So what we did here is this data here. This is the real part. We measure the real and imaginary conductivities at the same time. This is the real part here, and so it's a little bit sloping down, and we can hope to fit that and get out a scattering rate, and we fit that just the real part, and then if we use and that's a fit here to some particular temperature. We have the DC value, and we have the frequency dependence. So that green dashed line, that's our Drude model fit. And then we use those parameters, and we plot them here. And so that's what we would expect for the imaginary part if there was nothing else happening. But in reality, the imaginary part is way down here. So there's another contribution. And so when it doesn't contribute at all to the real part, the dissipated part of the response. And so if you ask if is it big or small, it depends upon what frequency range. At 1 terahertz, this dielectric contribution is of order which is of order the Drude part, the Drude response in the imaginary part.
God, thank you very much. It's very great. Thanks.
And Peter, if it's okay, there's one last question from Benjamin Walter.
Hi, Peter.
Hi.
Thanks for the nice talk. So I have a relatively quick question. So in the beginning, you talked about the Hall response as being sort of the goal of what you want to see, and then you talked about the magnetoelectric effect in 3D TIs. But in between, integer quantum Hall phases and 3D TIs, there's 2D TIs and quantum spin Hall phases, and there's this initial experiment on them with the conductance. But besides that, have you heard of or seen any proposals that you would feel are sort of in the right direction or useful for experiments for like a smoking gun or macroscopic effect in these things?
No, I don't think so. I don't know of any. Those original experiments are, of course, the ones in mercury telluride and everything which has come afterwards. It's those are beautiful experiments, and I think we should take them as face value for their claims. But they are those experiments, which are a linear response on a system like that. I think they suffer ultimately for the same problems that that these nonlinear responses on these higher dimensional systems suffer from interaction corrections, all kinds of non-idealities that are problems. So I don't know of one. There may be proposals, but I'm not aware of it.
Okay, great.
Yeah.
Thank you.
Peter, if I can just ask a quick question.
Please.
Sorry. So all these different phenomenology that you said would measure the barrier curvature, like the circular galvanic effect, nonlinear Hall effect, and this linear rotation. Are there other interpretations besides them? Like, is the fact that you see these direct, like it's a necessary condition of a barrier curvature, or can there be other trivial interpretation of these? I guess what I'm asking is, if you see this, is that a definitive confirmation?
Yeah. That's a good question. I think that for effects of these kinds, let's say, for instance, so there are extrinsic effects that can come in, right? So there are contact effects. There's Schottky potentials that can form between contacts. This is the kinds of experiments where people are illuminating with laser and trying to see the DC rectification signal. Those kinds of experiments, particularly, there's been some very good demonstrations of that, but they do have lots of possibilities for artifacts. And so there are all kinds of artifacts which have nothing to do with this physics. I think that it's fair to say that calculations of the bulk Chi2 response, for instance, calculating things like the shift current, are due of a 3D material, are due to these are always have to be taken in view of these Berry phase effects. It's essentially coming into the matrix elements for these excitations, and so those end up being very relevant parameter. Those end up being the relevant parameters in calculating it. If you look back at these papers that I referenced from the early 80s, there, in order to calculate these nonlinear effects, they were writing down the block functions and writing down, the block function in front and calculating everything in terms of block functions. What they didn't understand, of course, that there's a Berry phase structure that's associated with the block functions. But in those early papers, kind of the same calculation was done, but just with a very different language. And then that's 1979 or something, 1978. Those papers there, where again the nonlinear response is putting down as being written down in terms of these matrix elements, which take into account the block functions. Then Sipe has this remarkable paper from 2000 where he points out the correspondence with that all of this can be rewritten in terms of Berry phase structures. And then Morimoto and Nagaosa come in with this very nice paper where they basically show that there's a simpler way of calculating everything based on a Fluke formalism. So somebody on this call may correct me, but I think that's a fair statement that if we're talking about quantities like the 3D shift current, these are sensitive to Berry phase structures.
I see. Thank you.
Yeah. So if you see these effects, then it means that these Berry phase structures exist.
I see.
Which they do. You don't need to have a material which is topological, of course, as you well know, to have Berry phase structures, and even to have those Berry phase structures be interesting. In transition metal dichalcogenides, they're not topological, but the Berry phase structures are very interesting.
Okay, thank you. If there's no other questions, thank you, Peter, very much for this very nice.
My great pleasure.
Yeah, thank you.
We will.
And I look forward to continuing tomorrow.
Yeah. Thank you. Thank you, everyone.
Thank you.
See you, everybody.